How's that on? Are we doing the countdown?
That's good.
We're good? So what's with the crushed ice? Is that a new thing?
Friendship Club is giving them away.
Wow. Okay. Let's talk on the assignment from yesterday. Let's talk about that conversion where you have like 108 kilometers, whatever, it's like 32, 33, whatever that is. Okay? Now, so here's the deal. So I'm going to work through this because this is the most common conversion that you're going to do. Okay? So when you have 108, how many significant digits is this? Three, right?
Yeah.
No worries. So 108 kilometers, to kind of put it in perspective, is about 50 miles. Okay? So it'd be like here to about like 3/4 of the way to like Emporia. And it's like, how far is it? It's about 108 kilometers. It's like literally, give or take, about a half a mile. Okay? So this isn't a really precise measurement. It's 108 kilometers. It's a ballpark. Okay? It isn't like 108.000. It's 108. Okay? So we're going to change that into meters. So a couple of things that to avoid the pitfall of confusion. When you look at this ratio, this is not determining your significant digits. Don't look at this and go, oh, 1 kilometer only has one significant digit. Okay? Or this only has like one significant digit. This is an exact ratio. 1 kilometer is exactly 1,000 meters. Okay? So don't look at this and go, oh, well, this is limiting. No. The uncertainty comes from the initial measurement of 108. So this isn't bad. Get 108,000 meters. Okay? If you're into scientific notation, you can do 1.08 times 10 to the 5th meters. Okay? All right? No worries there. Everybody cool? Okay. Now, the next one is 1 hour. Now, on this one, I want to show you two different versions that you can do on this. Which one you choose, I don't care. Okay? So there's kind of a long way. And you can say, okay, hey, 1 hour is 60 minutes, and 1 minute is 60 seconds. Okay? You do the math, and you get 3,600. So, in terms of like a process, if you notice what I did with what was called technically like a factor label method, where you set this up, and then, if you go back over here, I did that same thing, over here, said, hey, 1 kilometer is 1,000 meters. Literally, don't shortcut this process. I've been doing these longer than you all have been alive. If you look at my answer keys, this is how I still work them. Okay? Literally, because you're going to eliminate a bunch of mistakes. So there's any number of promises I will make you. One of them being is that I will always show you the most efficient method and the best method first. I'm never going to show you one method and then have you come in the next day and say, well, there's actually a shortcut way to do this whole thing. I will always show you the best and most efficient way to work a problem. So why do you think after 20 some odd years of doing this, why do you think I still do it this way?
Because it's the best way?
Yeah, because it works. It eliminates errors. Okay? It allows you to see the process and just not the product. Now, the other way you can do this one is that you can just shortcut this and go 1 hour, 3,600 seconds. Now, here's the anomaly that I've noticed over the years. If you do this step, here's the most common mistake that's made. You all say that 1 hour is 360 seconds and not 3,600 seconds. And I don't know if you kind of think back and go, wow, a circle is 360 degrees and an hour, the clock goes around one time. I don't know, okay? But if you're going to do this, just remember it's 3,600 seconds, not 360, okay? All right. Now, last one. You got 120 kilometers per hour. So to give you some perspective, 120 kilometers per hour is about 70 miles per hour. Okay? So you're hauling the mail. If you're doing 120 kilometers per hour, you were hauling the mail. Okay? So, first off, written like this, 120 kilometers per hour. How many significant digits are there? Mr. Classic Truck Stop t-shirt.
3.
3, you sure?
No, 2.
3 or 2? You got a 50-50 shot?
I'm going with 2.
I think you should. Why?
Yeah. Because if there's a 0, you go to the first non-zero number. Right?
Kind of. How about if there's not a decimal place?
Oh, yeah, that's one.
0 decimal point. Yeah, decimal point is just a really, really small 0.
Mm-hmm.
Okay?
Yeah.
Okay, so, but that isn't there. So if there's not a 0, you count to the, for the first non-zero digit, you count to the left, right?
Mhm.
So this has 2 significant digits. If there had been a decimal place there, then how many significant digits would there be? Then there would be 3. Okay? So in other words, this is a ballpark. Okay? Hey, you know, how fast are you going? About 120, right? It's an estimate. I'm going about 120. Round numbers, right? Yes?
Now, if it had been 120.0, would there be 4?
Then there would be 4.
Okay.
If this was 120.0, okay, then you've got a really, really good speedometer. Because your speedometer estimates to the 10th of a kilometer per hour. Yeah, that would be a really, really good speedometer. And if you really get fancy, go, oh, now I have 5. Woo, aren't you special? Okay, but that's not what we got. So, this conversion is the most common conversion you will do in this class. I promise you, this is the most common one. I want to make sure everybody knows exactly how to do this. So you're going to set this up and go, okay, 120 kilometers, okay, right? Now, go ahead and put that over 1 hour. Don't put like the per hour up here in this cell. You're just going to get confused. Put 120 kilometers over 1 hour. Okay? Trust me on this one. Personally, I always get rid of the kilometers first and go, okay, there's 1,000 meters. Okay? Now, if I don't do anything else, great. What units would I have?
You would have meter per hour.
Meters per hour. Is that what I want?
No.
No. So I'm going to get rid of the hour. So I can go 1 hour is 3,600 seconds. Okay, kilometers cancel out. I'm left with meters. Hours cancel out to get seconds. Now, here's where you can shortcut this a little bit. Okay, so you can actually go through and like eliminate zeros, which you've learned to do if you ever had to do this by hand. So the short version is you take whatever it is in kilometers per hour, multiply by 10, and then divide by 36. Okay? It's the same step every time. So your shortcut, times 10, divide by 36. Boom, it works every time. Now, if you actually want to go through and do the whole deal, that's cool. So I promise you, on the test on Friday, you're going to have to do a problem like this, where you convert from kilometers per hour into meters per second. If you hand in that test on Friday, and you have not done this conversion, something's wrong. Okay? Something has gone horribly wrong. You got to be solid on this conversion just because we do it so often. So, somebody take 120, multiply it by 10, and divide by 36. Let me know what the oracle says. Yes?
Why is the 120, why does that 0? Oh, wait, because it's, right?
Why is what?
The 120
Yeah.
kilometer, why does the 0 not get crossed out?
Because the reason I don't count that as a significant digit is because I'm just saying this 0 right here is just a placeholder. So in other words, I know the 100. I just estimated the 2. I need the 0 as a placeholder. Okay? So this is why this just has 2 significant digits. I'm just saying I'm going about 120. It's a ballpark. Now, as opposed to saying, hey, I'm going 122. If I say I'm going 122, that implies a higher degree of precision than just a ballpark estimate of 120. Does that make sense? Yeah. We're cool. Okay. So somebody take 120 times 10 and divide by 36. What do you get?
33 with 0.3 repeating.
So you get 33.3 repeating 3, right? Oh, you go, oh, just write it all out, right? But here's the problem. And this is the biggest idea of significant digits, is that the door has to swing both ways. So Mary, if you see 33.333, right? How good do you think the data is? Just okay or really, really good data?
Really great.
Great, I have great, this is not good, great data. I have great data. But did I have great data to start with?
No.
No, I had a ballpark estimate, 120, okay? So I can't make this answer look better than the data that I have to start with, okay? So how should I write this answer then? Yeah, it's just going to be 33 meters per second, okay? Because I've got data, so I can only have an answer. It's a highly technical term, okay? Cool with that?
So how come with number 31, you were allowed to write it in scientific notation? Does that, like when you write it in scientific notation, does that make it look as if it's more like precise than it really is? Or
No. Okay, let me see your paper.
I was just making sure.
So on 31, you've got 108 kilometers, right? So here's the point. If you go back, I don't remember which one that was, okay? In scientific notation, you only show the values that are known, okay? Like, that are significant. So 1.08 times 10 to the 5th is showing the exact same number of significant digits as 108 does. It's the exact same number of significant digits. There is no difference. They both show the same degree of exactness. Okay? Good with that?
Yep.
Okay. Anything anybody wants me to go over? Anyone you're unsure of? Now let me take a quick opinion poll. Let me see, brother. On number 15, how many of you have the answer of 0.025 or 2.5 times 10 to the negative second? All right, you're wrong. We're going to correct this, okay? So here's the deal. So so you're subtracting on this one, right? So when you subtract, do you worry about the number of significant digits or place value?
Place value.
Least precise place value, right? Okay, least precise place value. So what am I asking you to subtract on number 15? What are the numbers?
2.67 times 10 to the negative second,
Okay,
and then
minus.
1.5 times 10 to the negative third.
Okay, now here's what you all are going to try and do. You're going to look at this and go, oh, this has 2 significant digits, and this has 3 significant digits. Therefore, my answer should have 2 significant digits. Okay, that's your mindset. But that isn't what we're about when you add or subtract. You're adding or subtracting, it's the least precise place value. Don't get the two confused. So the only way that you can really be for certain on this is if you write this out old school where you stack this up. So this is 0.0267, and this is 0.0015. So when I line these up, even though they don't have the same number of significant digits, they actually have the exact same precision. Okay? So since they both have the exact same precision, when I subtract this, okay, I've got to keep all of these. Okay? I've got to keep all of these numbers because when I line them up, they're both the same degree of precision. So this is what your answer should be on number 15. And if it's not, change it.
Same with addition?
Huh?
Same with addition?
Yeah, addition and subtraction is all about place value. Multiplication and division, it's all about the least number of significant digits. Okay. With that said, anybody want, if you're at all unsure about any answer, this is the time to ask.
Number.
Great.
13.
Hold on. 13?
Yeah.
Okay, let's talk about number 13. You got 7 points. Okay, so this might be a situation where this is like a rate function. It's so many newtons of force per unit of time. Here's the big question. Are you adding or subtracting or multiplying or dividing?
Dividing.
Multiplying and dividing. So what are you worried about? Precision or number of significant digits?
Number of significant digits.
Number of significant digits. Now, here, let me give you a simple true or false question, okay? True or false? Listen to me very carefully. True or false? You're comparing two different measurements. The measurement with more significant digits is going to be more precise than the one with less significant digits. Okay? So let me say this again. It's a true or false question. You have two different measurements. The measurement with more significant digits is going to be more precise than the one with less significant digits. So how many think that statement is true? This side of the room thinks it's true. Okay? So take it, the rest of you think it's false. Okay? Honus, why do you think it's false?
Well, you can have a lot of significant digits, but you could have that in the whole numbers, while the other one could be in the decimal point, making it more precise.
Oh, wow. Let's think about that. So let's say that you've got a measurement of 35820 meters. Okay? So you got 358,200 meters. Okay? So this might be like the radius of an orbiting satellite. This is how far above the satellite is above the Earth. And that's typically where the satellites are. Okay? Give you some perspective. So, how many significant digits does this number have?
4.
4. There's not a decimal place, so which direction do you count? Left. So I got 1, 2, 3, 4. 4 significant digits, right? It's a big number. Now, let's compare that to a measurement of 0.067 meters, okay? Which would be 6.7 centimeters, which would be about like yay, okay? So, this one has how many significant digits?
3.
2. It has 2. This is a decimal, so you
But
count.
it's a decimal place. Which direction do you count? Right. You find the first
yeah.
non-zero digit and you count everything to the right. So this only has 2 significant digits. Because if you were to put that in scientific notation, you would write it as 6.7 times 10 to the minus second. Okay? So, this only has 2 significant digits, but this number is much more precise than the distance to the orbiting satellite is. So this is a situation where I have a fewer number of significant digits, but it's a higher degree of precision than this one is. So don't confuse significant digits and precision. They're kind of related, but they're not. Now, so let's look at this, okay? Quick refresher on exponents. So a lot of times in physics, we're just happy if we get within what's called an order of magnitude. Order of magnitude means, hey, we're just happy if we get the exponent right. Okay, I don't care about the actual number. Like, for example, if you're trying to estimate the mass of the entire Milky Way galaxy, okay, it might be like, 10 to the 40th kilograms. If we're good with just 10 to the 40th, hey, we're happy with that. We're worried about, dealing with such a big number. Okay? Same thing on extremely small numbers. If you're trying to find the mass of a single electron, if you're 10 to the negative 31st, okay, if you get that order of magnitude right, hey, we're cool. So a lot of times in physics, because we're dealing with really big numbers or really small numbers, all we want to have right is the order of magnitude. So let's do a quick refresher on exponents. If I take 10 to the 10th and divide that by 10 to the 3rd, what is my order of magnitude on my exponent going to be?
10 to the 7th.
10 to the 7th. So as a ballpark, I should have something around 10 to the 7th. And I emphasize this again. When you're punching these numbers into your calculator, use that EE key or that EXP, sometimes it'll be like times 10 to the 10th. Don't punch this in as times 10 to the 10th. Unless you're very careful with your brackets, this is going to be a train wreck in terms of what you get for your order of magnitude. So, how many significant digits here? How many significant digits here? So your answer has to have 3 significant digits. Go with that. Anything else? Make sure that you have the right units. So you can just leave this as newtons per second. You don't have to simplify it down. You can just leave it as newtons per second. So it's like how much force is exerted per unit of time. It's a rate function. Okay, we're good? Going once? Honest?
Number 30.
Should have said it faster.
Number 30.
Number 30.
The cube root of 26s cubed.
Okay.
I just wanna.
Well, let's just talk about this, shall we?
Yeah.
Well, first off, I take the cube root of seconds cubed. I get what?
Seconds.
Seconds. So there's my units, right? So let's look at it this way. What's the square root of 9?
3.
Why?
Because 3 times 3 is 9.
Okay, so I want what number I multiply by itself 3 times gets me to 26.
It's gotta
Right.
be some decimal, yeah.
Huh?
It has to be some sort of decimal number. Yeah.
No, it just has to have 2 significant digits. But yeah, it is going to be a decimal. So it's going to be something. So look at it this way. 2 cubed is what?
8.
8. 3 cubed is
27.
27. 4 cubed is
64.
64. So it's got to be somewhere in that neighborhood. Okay? So this is why God made calculators, and you can just punch this in. Because it used to be, I'm going to sound old like I'm a dinosaur, and I am. One of the key things that we had to learn going through high school is how to do like square root functions by hand. Like you didn't have calculators. Calculators wouldn't do square root functions. So you would have to find, okay, hey, like what's the square root of 105? Well, then it just boils down to, okay, well, it's got to be something around 10, but less than 11, and then you just kind of go through an estimation process until you kind of get to where you want it to be. So calculators have come a long way. All right, now we're good. Anything else? Once, twice, sold. Get those handed in. So stop that. Good. Okay. So here's where we're at on our journey to physics enlightenment. So we've got the MKS system, right? 3 fundamental units, meters, kilograms, seconds. From there, we roll that into velocity, acceleration, force. Those units will get us all the way through kind of like, basically Thanksgiving, okay? Literally those 6 units, everything that we're going to make is going to be those 6 units until Thanksgiving. So then we said, okay, hey, we're going to graph stuff, independent variable, dependent variable, right? Dimensional analysis, here's what we've got going, okay? And then we figured, okay, well, how are we going to write an answer? All right, well, how many digits are we going to have? We've got to have units on it. So basically, you have all the tools that you need right now to do physics, okay? So now we just need to build on those tools and show you how to use them. So the lab that you're going to do today is kind of unique in the sense that I'm not going to tell you where or what your procedure is going to be. You have to figure out the procedure. So, but before that, you kind of have to give you a history lesson. So many, many years ago, there was a Greek philosopher named Aristotle. Aristotle was the student of Plato. Plato was the student of Socrates. And so this is like this long line of ancient Greek philosophers. If you ever get the chance to go back in time, go back and be a Greek philosopher. It's a sweet gig, okay? You get to wear a toga, walk around. All you have to do is just like argue with other philosophers. That's it, okay? You don't have to actually do anything. You don't have to produce anything. You just have to sit around and be a philosopher. It's kind of a sweet gig. Eat grapes. It's okay. So Aristotle had a tremendous influence on any number of topics, religion, politics, and even science, even though he wasn't a scientist. So in Aristotle's view, he didn't trust the senses. Because if you think about it, everything that you have ever experienced in this world came to you through your senses. Okay? Hopefully, your brain has had no direct contact with the outside world, which would be really weird if it did. So like for you to even hear me say the word Aristotle, I've got to form it in my mouth. I'm going to send out a series of compression waves. It's going to hit your eardrum. The eardrum is going to vibrate, sending the signal through the inner ear bones to your auditory nerve. Your auditory nerve is going to send that message to your brain. Your brain is going to pick it up and translate it into, oh, Bergkamp's talking about Aristotle. It's kind of cool. What you're able to see a white shirt because I've got photons that are being streaming out of the lights. They're hitting my shirt and bouncing off. They're going through your eye. Your eye is actually, it's a special type of lens. You're actually seeing me upside down because of the fact that you have a concave or convex lens. And so the back of your eye is seeing me upside down, but we've evolved to the point where we can flip it back over. right? So, and then you're seeing it, wow, these rods and cones are firing, wow, Burkamp's wearing a white shirt, which is even kind of weirder because, like for example, if you look at, like Bree's wearing a red shirt, here's the odd thing. Her shirt is actually every color but red. It absorbs every color in the spectrum, but it reflects red back off. That's why you see it as red. If someone's wearing a blue shirt, it absorbs all the colors but blue and bounces off blue. So McGriddle's sitting over there in a blue shirt because of the fact that it absorbs all the colors but blue. So his shirt is actually every color but blue, okay? Don't think about it, it gets weird, okay? I'm just telling you. So everything you touch, everything you've heard, everything you've smelled, everything has come to you through the senses. And in the Aristotelian view, your senses distorted things. So Aristotle said, look, the only way to really know what's going on in the world is to have a well thought out argument, the well-trained mind. So he was all about using your mind to think through problems, which was great for school funding because then you didn't have to build labs. Okay? They did no experiments in the Aristotelian time because Aristotle goes, hey, it's just a waste of time. All you have to do is think about it. Hey, you're good. So for like 2,000 years, that was the dominant way of doing science. All you had to have was a good argument. And if you had a good argument and you could convince everybody of it, that's all you needed. You didn't have to have the math, you didn't have to have the experimentation or anything else like that. You just had to have a good argument. Oh, okay, cool. So, one of the main things that he talked about is what's known as the law of falling bodies. And in the Aristotelian view, if you have like a larger mass and a smaller mass and you drop them, the larger mass in the Aristotelian view is going to hit first because he argued that, look, it's heavier, there's more of an attractive force on the heavier object. When you let go of it, because there's more force acting on the heavier object, it should fall faster. Okay, that was it. And everybody took that as the truth because this is what Aristotle said, because Aristotle had such a large influence on philosophy and religion and all of this other stuff. So for 2,000 years, no one actually bothered to do the lab. And you're sitting there going, for 2,000 years, no one bothered to take like two different mass objects and drop it. They had a lot going on. They had the plague, they had like Viking raids and Roman occupation of Europe, the Napoleonic Wars. There was a whole bunch of bad things that happened. They didn't even have Oreos at the time, so they had other things to worry about. So along comes Galileo, okay? Beginning of the Renaissance. So as the story has it, and I don't care if it's true or not, it's still a good story. According to the legend, Galileo goes to the Leaning Tower of Pisa, and he has a small cannonball and he has a large cannonball. And this is like this festival. So this place is full of well-educated people who all would have studied Aristotle's views on science and the law of falling bodies. So as the legend has it, Galileo goes out to the Leaning Tower of Pisa, and he drops these two cannonballs, and lo and behold, they hit at the same time. And everybody goes, oh my God. And people were not happy about this because it was almost like blasphemy. Because it isn't like he disproved Aristotle in a lab and then he published a paper. He did it in a very open way that made Aristotle look like an idiot. Okay, because this is one of his main tenets. But and you wouldn't think that would make a difference, but here's the reality. That completely shifted the pendulum in science in terms of how science was done. So for 2,000 years, all you had to have was a well thought out argument. That was it. That's all you had to have. As soon as Galileo did this, the pendulum swung to the other side. And they said, okay, hey, if we're going to accept anything, we've got to have proof, we've got to have the math behind it, we've got to be able to do an experiment that has to be able to be replicated by other scientists. Okay, and that's the modern scientific method that we have right now. So because of that simple deal of dropping the cannonballs, the pendulum swung over to you have to have experimentation. So here's the classic example. Law of conservation of mass, which you all studied in Chem 1. This is what allows you to balance equations. Mass of the reactants equals the mass of the products. Okay, you all studied this. A guy by the name of Antoine Lavoisier, a French chemist, was one that actually proved it. Now, you would think if there's anything that would just intuitively make sense, hey, that makes sense. Hey, here's the mass of the reactants actually equal to the mass of the products. Even though it made sense, no one was going to accept it until it was actually proven. Now, unfortunately, he was on the wrong side of the French Revolution and got his head cut off by a guillotine. Sad story. But great in science, not so much in picking the right side in a political fight. Too bad. And if you ever get a chance, there's any number of like weird characters in science. Lavoisier was one of them. So, and we'll talk about other ones as we go along. So, at this point, everybody's got to be able to do experimentation. So here's what you're going to do. You're going to work together as your typical lab groups. You're going to hand in one lab write-up for the group. Okay, this is going to be important. This is the only time you will ever do this. Okay, and only one time. Now, here's what's important for you guys. To make this like a real science endeavor, I'm going to give your labs to my first block class on Thursday. And they're going to build whatever you tell them to build in your procedure. And they're going to try and replicate your results. You guys are going to do my first blocks class. Okay? So when you're writing up your procedure on this deal, you have to keep in mind, number one, it's my first block class. It's early in the morning. They're half asleep. I'm just telling you. So when you're writing up your procedure, make this as crystal clear as you possibly can. So here's your challenge. You're going to try and figure out who was right. Was Aristotle correct that heavier objects fall faster? Or was Galileo correct that all objects fall at the same rate regardless of mass? So you're going to have a single penny, a bundle of 5, and a bundle of 10. So what you have to do is develop a timing device that allows you to measure time. You have to build something, okay? Creativity is part of your grade. So if you look at that grading rubric, which I have down at the bottom of the page, first thing, statement of purpose. What's the purpose of the lab? Hey, we're trying to prove who was right, okay? If you want to have a list of materials, you can, okay? It's recommended but not mandatory. The heart and soul of the lab is going to be the procedure. So you've got to write this procedure so that somebody else, my first block class is going to be half asleep, can read your procedure and build what you built. And then they should get the same results that you get. Now, if you want to take your phone and take pictures and incorporate pictures, hey, great, fantastic, okay? Not a big deal. Part of your lab is also going to be creativity. Now, let me give you an example. This is 0 creativity points. But let's say you say, hey, I'll build a pendulum. Okay, cool. So you're going to take a piece of string and you're going to tie a piece of metal on the end of it, and you're going to hold it up like a pendulum, and you're going to let go of it, okay? So Max is holding up the pendulum. Honus is standing on top of the table holding the penny against the ceiling. Honus lets go of the penny. Max lets go of the pendulum. Max sees where the pendulum has traveled when the penny hits the ground. So their measurement of time would be like how many degrees the pendulum swung through while the penny was falling. So you're going to make some other event happen that you can record while the penny is falling from the ceiling to the floor. You might, I've got bicycle wheels, I've got pulleys, I've got weights, I've got ramps, I've got balloons, straws, I got a string, a whole bunch of stuff back there. So you've got to build something where an event will take place that my first block class can build and replicate. So as you're doing this, I would recommend that you do at least 5 trials for each set. Like 5 trials for a single penny, 5 trials for 5, 5 trials for 10. Keep in mind everything that we've talked about. Be consistent with your precision. If you're going to measure everything out to the tenths, hey, cool, measure everything out to the tenths. Don't change that. Then when you find your average, make your average out to the tenth. Be consistent in how you record your data. Be very careful about how you write up that procedure. Because if you just say, hey, all right, take a 1 kilogram mass and set it on the table, and that's all you tell them to do, you don't tell them where to set it, I'm going to tell first block, you get to choose wherever you set it. And if you don't tell them how to set it up, hey, maybe they're going to lay that over and go, oh, hey, here's a 1 kilogram mass. Because there's a big difference between a 1 kilogram mass laying on its side and a 1 kilogram mass setting up. So this is the beauty of pictures. They're worth 1,000 words. So you all have Chromebooks, okay, which I'm guessing you all have the technology to share documents and incorporate pictures. That's cool. You can do pictures. I highly encourage it. It takes out some of the guesswork. So you're going to have the rest of the time today. Then you're also going to have probably about a half an hour tomorrow to finish that up. But listen to me, because my first block is doing this. Listen to me. I have to have these labs before school starts on Thursday morning. Not during class, because I got to have your labs so first block can do them. Okay? So I have to have these labs before school starts Thursday morning. Okay? Now, y'all can share documents, y'all do whatever voodoo that you need to do. Maybe have somebody do this, have somebody do that. Look at the grading rubric. Make sure you have all of those things. So the main part of this is that you're going to get your data and you're going to write a conclusion. You're going to say, okay, hey, Galileo was correct because there wasn't any difference. Or maybe you realize, hey, according to our data, Aristotle was right because we see a difference in the times. Or maybe your data is so jacked up that you don't know what's going on. It's like, we have no idea who is right. Our data is all over the place. We got nothing. And sometimes that happens, okay? You laugh and scoff because you all think, oh, scientists always get it right the first time. Oh, for the love of God, no. Right? Look at the whole fiasco with what's the center of our solar system. Is it the Earth? Is it the Sun? What is it? That took a long time to straighten out. So it isn't like scientists had this thing right from the get-go. You know, we made some big mistakes along the way. So it happens. Sometimes you just get jacked up data. So I'm done. Go back there. You've got all of that stuff. Use whatever you need. If there's something that you don't have, ask me. I'll try and get it. So this will be for tomorrow. This is a review of everything that we have done. No, there's not a backside to it. Okay? So something like 15 questions. It's a review of significant digits and all that good stuff. So this is due tomorrow. Okay? All right. Now you can stop.